So hi, everyone. It's a pleasure to be here to present our paper GemNet. And this is co-work with Tonghan and David. And Tonghan just told me again to emphasize that he can't come here due to visa issues. It's really unfortunate. So wait, this is okay. So I guess all of you are very familiar with this, but just to go through the basics of auction, we adopt a independent private valuation model where each agent has a private valuation of items. They submit a bid, a mechanism is run determining an allocation and payment rule, and a utility for an agent is realized after the allocation and payment rule. So the key thing here is what we say incentive compatibility constraints. And here I use the dominant strategy incentive compatibility constraints, which says that no matter what the other bidders report, truth telling should always be the weakly dominant strategy for this bidder. And of course, there's also the individual rationality constraints, which holds that the bidder can walk away with less than zero utility. So what it means here is that in this example that we have, we see that the first price auction is not strategy proof or DSIC in the sense that the second bidder can simply deviate to a lower bid here, like for example 6.01, so that he still walks away the item with a lower price. And so this is not that desirable, and we think that a simple fix might be to implement a second price auction instead, where the winner gets the second highest price in the auction. And so here, when we see that in the second price auction, no matter how he bids, like 6.01 or $10, he still walks away with the item with $6. So this is what we call set strategy proof or incentive compatibility, basically saying there's no useful deviation for that agent to misreport his true value. And so with this incentive compatibility being a very important focus, we're naturally asking the question, well, of all the mechanisms, auction mechanisms that are incentive compatible, what is the revenue optimal one of those? And Meyerson famously solved the problem for selling a single item in 1981. But to this date, if we consider notions of DSIC only, the analytical results have not been that many. We only have variations on the single bidder setting and the setting with two items, but only two possible values in their support. And so with all these analytical difficulties, there has been a lot of computational approaches aiming to solve the problem. And again, it's worth to mention that there's a ton of wonderful work on the BIC setting, but we're mostly concerned with the DSIC setting. But in this setting, each of the computational works are limited in one significant aspect. RegretNet and ElkNet does not achieve full strategy proofness. They minimize a regret, but they do not push it all the way down to zero. RochetNet and ManuNet are single bidder approaches, so they do not work in the multi-bidder setting. And a ManuNet and Valkyrie AMA confine the search space within affine maximizer auctions, thereby losing expressiveness. So we really want the middle of this picture that is both expressive, multi-bidder, and fully strategy proof. And this is what our GemNet does. So at a higher level, we start by asking ourselves the question, so how does RochetNet guarantee strategy proofness? The way that RochetNet guarantees strategy proofness, and RochetNet only works in the single bidder setting, is they adopt the menu-based representation. So quick overview of what the menu-based approach is. So a menu-based approach basically is that we have a fixed menu. So I like to think of the analogy where you go into a restaurant and you get a fixed menu and you tell the bidder, okay, this is my valuation, and the bidder chooses the item for you according to what you report to her. So it's easy to see that this is strategy proof because first of all, however you misreport, you are getting the same fixed menu. And you also want that you get the right item, the right choices is made on your behalf. So it is in your best interest to report your true value. And so this is the single bidder setting. We first note that it is easy to generalize this to a multi-bidder setting. In fact, it's famously known and shown in 1979 that a mechanism is strategy proof if and only if there's a menu representation that is, first of all, self-bid independent. in the sense that when you change your bid, you get the same menu, but also bidder optimizing. Again, you get the best menu according to the bid that you report. And so it's easy to come up with a framework like this, where the other bidders' bid are used to generate a single bidder's menu. And then the best item according to the bid is given to that agent, to the bidder. But here's a problem, and you directly see it from this graph, which is what we call over-allocation. Essentially here, we are over-promising the item where we only have one of that item available for auction, but we are promising with probability 1 to the first bidder and probability 0.5 to the second bidder. And this is, in fact, also a problem when we have multiple items and multiple bidders. In this example, we have acorn and bamboo sticks for sale, and we have a squirrel and a panda. We see that in this example that I have, we are over-allocating the first item, promising it both to the squirrel and to the panda. And that forms a problem. And a naive solution that we can come up with is, okay, so now we have over-allocation on the first item. Why don't we just normalize it, for example, using a softmax, or find whatever ways to squeeze the one item into the two items that we promised. But this is not going to work, because in fact, the reason that why we have incentive compatibility through the menu-based approach is that the best item according to the bid is made on the bidder's behalf. But when we kind of changes the item after we decide what to allocate, it changes their original incentives. And here you see that the item that is actually given this to the squirrel gives him a very, very low utility. And there's actually a strategy for them to misreport so that they actually just walk away or they choose some other item. And so this is a problem. And we call this an over-allocation problem. So we need to ensure, so what do we actually want? We want to ensure that when all bidders report truthfully, there's no over-allocation, in the sense that we craft our menus in a way that however they report, they point their bidder optimal item towards a point where you aggregate together all the bidders, you don't get an over-allocation. And this seems pretty hard to do, but it's actually quite simple to do using a neural network-based approach where we train a neural network where we take the other bidder's bid as input and we pick the optimal item according to its bid, but we train it with a loss that are comprised of two parts. The first part is the negated revenue part, which aims to maximize the revenue for our mechanism. And the second part is what we call an incompatibility loss part, which just aims to lower the occurrences of this incompatibility or over-allocation. So after this deep learning step, we already have a mechanism that achieves fairly high revenue with very low over-allocation occurrences. But this is still not fully desirable in the sense that we don't even want any over-allocation. Essentially, what does it mean for a mechanism to sometimes over-allocate the item, even if it's like 0.001% of probability? And so we have to think of ways that we adjust. And I've mentioned this, that like the outcome, the mechanism that we arrive after this state is already pretty good. So we only want to make tiny adjustments in order for it to work and make it fully strategy-proof. So we aim to get another step, which is to get this over-allocation probability down to 0. And to do that, we propose a mixed integer linear program that does price adjustments. Essentially, the price adjustments, you can think of making the tiny adjustments from the deep learning results that we get in our first step, but getting the infeasibility all the way down to 0. And the difficulty for using an MILP lies in the fact that our valuation spaces are all continuous. But in order to make it feasible, we have to work under finite spaces. And so we will have to discretize the state space. And so here we discretize it into a set of grid points in this continuous space. And the thing to notice is that we don't only want compatibility or no over-allocation to hold on these grid points themselves. We want it to hold actually on any point in this continuous range. So there's the two parts of the goal, that we want to ensure compatibility on the grid point, but also on any point of the grid. So what do we do? So here we can start with any grid point, and this is the menu for the agent that we are doing the price transformation for. And let's for us suppose that we fix v minus I, and we fix their choice in utility. So here the squirrels are getting the acorn at price 6, and this is fixed. And so we only think about the menu and prices, the allocation and prices we give to the panda. And we see that here there's an incompatibility in that we are over allocating the acorn. But then let's think about how much prices we'll need to adjust in order to push it to a feasible element. We see that here, if we make this $1 adjustment here, we can push the utility in a way that the panda are now preferring the option which doesn't create an over allocation anymore. So this is an easy adjustment that we can make. But this adjustment might be very ad hoc to this grid point itself, in the sense that if we consider a value, a point very nearby this grid point that has a tiny valuation differences, and this difference is resulting in the panda having a tiny little bit more preferred utility on the first item, you get this, again, we get this over allocation. So our overall idea is that, and it's worth mentioning that there's another way in which this can change, which is that, and before we mentioned how the value changes, and here is another case where the other bidder's value changes. So here we are plotting v minus I, and here v minus I is one bidder. Essentially, when the other bidder moves away from their grid point to a nearby neighborhood, the menu that this panda gets changes a little bit. And here we see the prices actually changes by a little bit. And this is because of our neural network framework. And because it changes a little bit, we also push it to a element that creates an over allocation. So essentially, we want to handle both of these changes. And there's two parts of how the utility can change. The first part is how the menu changes within the neighborhood. And the second is how the value changes. And for how the menu changes, we can bound using network Lipschitzness. And for the value changes, we can directly analyze the distances between the center of the grid point. So here what we do is that we not only increase it by 1, as in the previous example, which is the minimum amount to make sure that no over allocation hold on this grid point itself, we increase it by a little bit more than that. And this amount, which is what we call a safety margin. So essentially, this safety margin of 0.3 here is structured such that however these 2 points change, and let's just assume we only have 2 agents right now, but however they change around the grid point, we always have this feasible element on top. And this is how we guarantee that we have feasibility. And through the menu-based representation, we also have strategy proofness as well. And this is a fully specified mechanism. So just a brief outline of this second step. The objective here, this is also something worth mentioning, we're just minimizing the price changes from the deep learning results. And this is how deep learning really comes in the sense that we need this initialization to make it really work, and we are only adding tiny adjustments on top of this, subject to the constraint that we have the safety margin such that however the points move around the neighborhood of their grid point, we still have feasibility, as well as the typical IR constraint. And so with this, we can guarantee complete feasibility in the region. So one natural problem to ask is that whether using an MILP seems pretty slow. And we noticed that we've had a lot of tricks in our paper to actually speed this up. One very useful trick we use is to utilize the IR condition. Essentially, a lot of the menu options that we get for the agent after deep learning steps already give a negative utility. And if we are only concerned with ourselves and making positive changes, we can disregard all of them together. And it might come as, it might seem like a limitation to only limit it to positive price changes. But because of the fact that we are only aiming at making small adjustments from the deep learning results, at least empirically from what we observe, this is not really affecting the results that much. And using tricks like this, we're able to reduce the number of variables and constraints we needed by 99.9 something %, making it really tractable to run these MILPs in the settings that we consider. And so this brief overview over our results. First of all, we are able to get better revenue than other strategy-proof baselines, like using a fine maximizer approach, and we're able to get revenue very close to RegretNet, which is not fully strategy proof. There's a positive regret. And we're able to handle not only the uniform distribution, but also beta distributions. But in general, because we are using the differentiable economics approaches, just sampling from the distribution, we are not really confined in any like particular distribution spaces. We are also able to recover the optimal mechanism from Yao in 2017. And this is the only known multi-bidder analytical DSIC results that are available. We're able to get their results. And also, if you look at the allocation rule that we've learned, the first column is the optimal one. This is what we learned. We see that it is like what AManuNet and RegretNet learned are indeed a little bit different from the optimal, even though they achieve, look at the graph, they achieve somewhat close revenue to the optimal ones, but they are learning a different mechanism. And it is probably more significant if you look at this graph, which we consider the 2x2 settings drawn from a uniform distribution of 0, 1. We see that this is our allocation rule before transformation, and this is after transformation. And if you look at these dotted lines, you see really what this transformation does. It is just pushing a mechanism that is already very close to what we get in the end by a tiny bit. And this tiny bit is needed to ensure feasibility across the entire range. And we see that we learn a different allocation rule from AManuNet. Again, this is quite interesting because AManuNet has close revenue guarantees. It's smaller than us by a little bit, but they learn a kind of a different mechanism. And we are getting results that are very structurally similar to RegretNet, but by the nature of RegretNet, which had positive regret in the end, you can see that the boundaries are a little bit blurry, whereas we get these like very nice separated boundaries. And this is another example that I think is quite interesting. And this is the case with 3 bidders and 3 items. And the left is shown for a optimal allocation we know for a single item, single bidder, 3 item option. And this is what is known as a straitjacket option. You can see the allocation roughly looks like this. And here's what AManuNet learns. And to make a comparison to this, we can actually hold the second and third bidders bid constant. And so we see this is what AManuNet learns, this is what RegretNet learns, and this is what our mechanism GemNet learns. Again, it's hard to argue about optimality here and then not making the statement that this is the optimal mechanism. But again, we do achieve better revenue than AManuNet and better strategy proof guarantees from RegretNet. And this is somewhat interesting because the mechanisms that we've learned here are very similar to the optimal straitjacket option allocation. And in our paper, we have an illustration where we actually changes V2 and V3. We see these regions change, but the overall shape remains constant. And we think that these are interesting observations. We weren't theoretically equipped enough to make a duality argument to prove optimality, but we hope that this goes in that direction in the sense that it will potentially highlight changes like this. And something that I just think is worth mentioning about scaling, the largest instances that we tried is like the 2 to 10 settings. And in general, we tried settings like 2x2, 3x3, 2x5. Because of the nature of mixed integer linear program, it does scale exponentially. So we do have a problem with scaling up. If we think of a setting with like 10 bidders and 10 items, this is a current limitation of our work. But we do think that if we just limit ourselves to finding what these allocation looks like, we don't necessarily have to use the mixed integer linear program step. And if we don't use that step, we already are able to get the pre-transformation result. And this has less variation to scale. So this can scale quite well. This, because it uses a mixed integer linear program, doesn't scale that well. So there's a problem with scaling, but if we only want to get the rough shape and to understand what the mechanism probably looks like, we can also scale it up to reasonable size instances. And so this is all that I have. Thank you so much for listening. And just to mention some of the future directions that I think combinatorial auction is one easy one, more better ways to handle price adjustments and scaling to larger instances might be also interesting direction. Thank you so much for listening.